All right, now this year I have changed a couple things from last year. One of them is I've been wearing a suit coat to try and be a little more pretentious, and people may listen to me a little more attentively if I'm dressed more nicely. But in honor of the holiday, I wanted to show everybody my holiday sweater, so I'm going to kick off my... So there's a dinosaur and some reindeer and a little puddle of blood or something, I don't know. So good morning, science lovers, and happy holidays. One of the other things I've changed, I got a question about this yesterday from my best friend, who said, why are you printing out things for your talks? Because you always used to just wing it. And one of the best reasons for doing that is because I get to have fewer words on my slides and more pretty pictures. Well, pictures, I don't know if they're pretty. Let's see if this works. Whoops. Mike, can you maybe put the focus on the slideshow so the mouse works?
What do you need?
Yeah, just click anywhere in this blue area with that mouse pointer. Thank you. That's it.
Okay.
Yeah. All right. As always, my thanks to the Humanists of West Suburban Chicagoland, of whom I am a board member. And we have at least 2 other board members here this morning. Those of you who didn't join us for our holiday Human Life celebration missed a rip-roaring good time. Don't worry, we'll do it again next year. We've got some songs that have become traditions, and hope to see you in some of our humanist-specific meetings. Coming up in January, we're going to have a guided discussion about Islam and religious violence or religious extremism. And we've got Dr. Hasabala, who's a physician in Chicago and an author of a nationally prominent blog called God, Faith, and a Pen. He will be joining us. We've got Jason Heap, who is the national head of Coalition of Reason. He's coming in from Washington, D.C. He will be part of our guided panel. And then the local minister from this church, Reverend Tom Capo, will also serve as a facilitator. That's going to be the second Wednesday of January at 7:30 p.m. Please join us if you're interested, and tell people who you think may also be interested. Speaking of this church, the DuPage Unitarian Universalist Church, we are very grateful to this church for providing facilities, keeping the lights on, etc. I don't see the bowl back there, but we certainly welcome any donation that you can provide that might help ensure that this remains a viable institution. All right, we've got a website, YouTube channel. If you do a search for Humanists or Quest, the name of this series is the Quest series, you're likely to find our YouTube channel where we have videos of nearly every talk recorded, and there for those who couldn't make it. All right, today's topic was kind of intentionally misleading isn't the right word, but I wanted to construct it in such a way that we might get people in the audience who are particularly intrigued by the notion of Gaia and what's called the Gaia hypothesis. The Gaia hypothesis, stated briefly, is that the life that exists on this planet works in concert with climatological, oceanographic, geologic processes, atmospheric processes, to continually maintain the planet in such a state that it is almost perfectly suited to the life that is upon it. So it's this idea that there's this very complex feedback mechanism between the planet and the ecosystem it supports, and that they are mutually reinforcing. Sometimes people have gone a little further and characterized the Earth itself as a living organism. I think that is a bit extreme, but we'll talk a little bit more about that as we go today. So my secret agenda, though, the actual bulk of this talk is going to be about geology. If I just said, today's talk is about geology, I might not have gotten as good a turnout because rocks are boring, some people think. I tend to disagree. Here's some beautiful rocks from Gansu, China. And you can see clearly the sedimentary layers here and the colors. Those colors come from particular kinds of mineral deposits. And they provide incontrovertible proof that the Earth has been around for a very long time, and that there have been weathering processes that deposit sediments in shallow seas and bays and whatnot. And so the history of Earth is kind of written in the rocks. And life has left its inscription on many of the pages of the history of Earth, and we're going to talk about that. So geology can be quite wonderful. Life, again, leaves its imprint on the book of life, the book written in stone. And it also impacts the atmosphere. So life and stone, earth, sea, and air work together with life to form a complete whole. You cannot typically understand one of those systems without understanding the entirety. That's the Grand Canyon, by the way. So I want to talk a little bit about feedback cycles. A feedback cycle can take two forms. It can be positive feedback and negative feedback. All right? I assume that there are many of you who have seen pictures of the Galloping Gertie. The Tacoma Narrows Bridge that got into a resonance with some blowing wind, and it started bucking higher and higher, and eventually the whole bridge collapsed. Those kind of systems constitute a kind of driven system, where as long as you have an input, even if the input itself is fairly constant, it can lead to an ever-increasing response. The motion of the bridge provides momentum to the moving bridge, and then the wind imparts even more energy to the moving bridge, which builds on even more momentum, and you get this kind of positive feedback loop. So feedback can take the context of a positive loop, where it's self-reinforcing. This is an example of that kind of phenomena. The graph, or the picture of Earth you see here, is a picture of, I believe it's Earth's albedo, or reflectivity, the radiation energy coming from the Earth. And as you might expect, near the poles, it's less than it is near the equator. That kind of thermal signature for the planet also is implicated in the rate of evaporation. This is a map compiled from satellite data that shows evaporation rates in different places on the planet, on the oceans. And as you might expect, the evaporation rate at the polar regions is less. One of the things that leads to is the temperature and the amount of warming on the land, right? The precipitation on the land, the amount of water vapor in the air, and that drives the amount of cloud cover, right? And so this gets into this idea that you can have kind of an insulating blanket of clouds and other kinds of atmospheric particles that trap some of the warmth. And if that traps some of the warmth, then that leads back to the first picture that shows the amount of warmth across the surface of the Earth. So it's a self-reinforcing process. It warms the Earth, causing more evaporation. More evaporation causes more water vapor in the atmosphere. More water vapor leads to more clouds, which can trap some of the heat, which leads to a warmer Earth, which, right, you see the cycle? But interestingly enough, there's another set of phenomena called negative feedback cycles. And in negative feedback cycles, whenever a change happens to a system, it tends to be dampened or lessened by some response of that said system. So here's an amount of water vapor, potentially, which, interestingly enough, correlates to the evaporation rate. I think this may be the heat signature. Yeah, the evaporation rate, which has to, evaporating water cools things off, right? So now we've got a negative impact on the temperature of the surface of the Earth because evaporation cools things. And as it forms cloud cover over the Earth, the clouds tend to reflect heat back into space. So clouds don't just form a blanket over the lower part of the atmosphere, they actually block some of the sunlight from coming in. So clouds have a reflective property that can tend to cool the Earth. So which is it? Do clouds cool the Earth or do clouds cause the Earth to warm up? Well, part of what is so difficult about climate science is to untangle the relationships between these and to quantify them correctly so that you understand which part is more prominent over which time spans and which geographies. So feedback systems can become incredibly complex and difficult to sort out. One of the feedback mechanisms that's active on Earth that doesn't involve the atmosphere is something called bioturbation. You perturb, right, to disturb. So bioturbation is the work of worms and undersea creatures, insects in the soil that turn over the soil load and that fertilize the soil load. And if you get that happening for several million years, or tens of millions or hundreds of millions of years, you might expect that that physical and chemical process of changing the soil of the Earth leaves its imprint in the geologic record, and we do see that that's the case. So there are feedback mechanisms that don't just entail the atmosphere. The very Earth itself is subjected to changes from life. One of the things I didn't talk about in this slide is the vegetative cover, right? Everybody knows the standard narrative about climate change, and one of them is that deforestation impacts things, the amount of algae in the ocean, which absorbs sunlight and CO2. All of these things are very complex, and untangling them is difficult. So life has an impact on climate as well. Life also has an impact on the soil. But, you know, people are cheery. I tend to love people. One of the things that I enjoy studying is brain science and cognitive science and psychology, right? If you're like me, you're interested in nearly every aspect of the natural world. And one of the things that I've found is that people tend to be, on a whole, more optimistic than is warranted. Also, people tend to think that they have more control over their own individual lives than is accurately true. But that kind of optimism seems to serve our species well, and certainly serves our mental health well. We are possessed by a kind of transcendent optimism that the Earth will be all blue skies and green fields indefinitely into the future. This optimism can evidence itself in several different ways. With regards to the Gaia hypothesis, some people believe that there is some kind of magical force in the universe. You may call it God, you may call it the Force. We saw the Star Wars movie recently. Good movie, by the way. But there's this transcendent, perhaps even being in the universe that is a caretaker for our planet and is full of love and joy and making sure that everything always works and it's always perfectly suited for humanity. Well, as a member of a humanist group, I can tell you that I don't subscribe to that point of view, and I suspect many of you don't as well. But even if you do subscribe to the idea that there is some kind of transcendent force in the universe, that doesn't abdicate us of our responsibility to understand the natural world and to take some accountability in its maintenance and propagation through time. So that idea can make a lot of people happy. Another idea that makes a lot of people happy is this notion that the Earth has a kind of spirit to it, that Gaia is a notion that the Earth is a single unified living system that the bears and the wolves and the cougars and the oceans and the sky and the mountains all work together to create this beautiful harmony that is self-perpetuating, and nothing could ever go wrong with it because it's just so much stronger than human beings, this beautiful natural system. And woe be unto us if we perturb it or act upon it in any kind of way. Well, I believe that this is also kind of a fairy tale. The Earth is a physical, biological system. There's no guiding directive. There's no purpose behind it, right? There's no cosmic law that says the Earth shall support life for the next 2 billion years until the sun expands to the point that the oceans boil off, right? There's no law of nature that says anything like that. And then there's a slightly more scientific idea that the earth, air, life, water systems, the geologic systems of the earth all work together in collusion to keep the earth as a habitable place. And of course, this makes us happy because it provides a sense of optimism about the future. But when you look at the reality, oftentimes you see what's going on in the world around you, and you perceive very large-scale deviations from what might otherwise be a natural progression of biologic and perhaps hydrologic or atmospheric phenomena. So human beings are beginning to become a force of nature. And this is going to be very relevant, not even only now, but even more so in the future. You can start to see the impacts of humanity on large scales. And there are some scientists who say that because of the impact of humanity and our technology, we've actually entered a new geologic era, the Anthropocene, the human age. And I don't know yet if there's a universal consensus about it, but there's a good argument to be made for it that we are in fact in a new geologic and biologic age. That there's a book out, Mike referenced it a while back, The Sixth Extinction, one of the best science books of the past year, and it talks about partly, the impact of humanity on our biosphere. All of these things are enough to make us sad. But there is still a case for optimism in the fact that we can understand the world. We can sort out some of these complex processes. We can begin to understand what the impacts of our actions are on our planet. The interplay between life and Earth. So one of the best ways to learn how to do something is to look at history. Right? The old famous quote, was it Benjamin Disraeli, that those who forget history are doomed to repeat it. I may not have the source right, but you can apply that same kind of thing to looking at the history of Earth, what has happened and why. So let's briefly go through the history of the Earth. I can't go step by step because that would take about 3.8 billion years. But the Earth started as a glowing cinder, as it were, full of magma, roiling magma, bombarded by rocks from space, the largest of which caused some of the outer crust of the proto-Earth to frisson off into the moon. When you look at the composition of the moon, you see that through and through it's made essentially of the same stuff that the surface of the Earth is made out of, essentially basalt. So we have pretty good evidence that the moon was sloughed off by the Earth when it collided with another body in the solar system about the size of Mars. So the early Earth was hot and chaotic. That was about the first 50 to 100 million years. And then we get the blue Earth, where water starts to condense out of the atmosphere and water vapor is outgassed from the interior of the Earth. You get comets that hit the Earth. Comets are often loaded with water. And after about 100 million years, you start getting a water world. But there's no land at this point. Where does the land come from? Well, that starts to happen in a phase that Robert Hazen, whose book I used for a lot of the material in this talk, I'll talk more about his book in a minute. Robert Hazen calls gray earth, where granite starts to form. So if you look closely at this globe, you see little rocky islands. In geologic contexts, you see things like the arc of the Hawaiian Islands or the arc of Japanese islands. And billions of years ago, that's what all the land on the Earth looked like. But if you start having volcanoes that spew out some of the lighter material that comprise the material of the Earth, that sort of floats on the surface of the Earth. It doesn't float on water, but it floats on the heavier basalt underlying much of the crust of the Earth, and it builds up mounds. And then those mounds move together because of plate tectonics. We'll talk more about that in a minute, and form the earliest continents. But one way to think about the way that those island granitic arcs form is if you look at a pot of roiling iron, you'll see that there are some there's some crust, there's some impurities on that molten iron. Well, the Earth has a molten iron core as well, and the impurities that are things like silicon and carbon and whatnot tend to float up to the top. So we've got the lighter elements comprising the crust of the Earth and the heavier, denser stuff down below. Even basalt, which I've mentioned a couple times already, basalt is denser than granite. And we think about mountains being soft and solid and very hard and durable. Well, in a geologic context, granite is relatively soft compared to most of the rocks that would form naturally through the aggregation of chemicals in the early Earth. So this, this gray Earth, the period of island arc formation and the formation of the cores of many of the original continents, lasted until the Earth was about 1 billion years old. Starting about that time, and hence, there have been supercontinents. Some of you have heard about Pangaea or Gondwana. Some of the ideas that there were supercontinents that came and went on the surface of the Earth. And it's likely to continue for at least 1 billion years or two longer, that continents will come and go. There was another interesting period of Earth about 1 billion to 2.7 billion years ago, and that's called red Earth. Something very interesting happened during this period. So I told you that we have an iron core to our planet, and there's all kinds of evidence to support that contention. But it turns out that iron is pretty soluble in water. It dissolves in water as long as there's not much oxygen present. If there's oxygen present, then dissolved iron turns into rust. And rust, as we probably see from direct experience, doesn't dissolve in water. So once you start getting enough oxygen in the water, and perhaps even in the air, then the iron begins to precipitate out as rust. In fact, the scale of this phenomena in Earth's geologic history is almost inconceivable. Almost without exception, the iron that we use today is mined from sedimentary rock. I mean, the idea that iron can form sedimentary rock might be a bit astonishing. It was to me when I first encountered it. Iron is solid and tough and strong, right? But it's actually in sedimentary rock. There are these things called banded iron deposits. And these banded iron deposits speak of a geologic era when iron precipitated out of the materials that were weathered from the land and from the ocean. But remember, there was a prerequisite for that to happen, and that prerequisite is the existence of oxygen. Well, it turns out, as I think I said last year when I was talking about nucleosynthesis, the way elements are made from stars, oxygen is one of the more gregarious chemical elements, similar to carbon. Carbon will bond with nearly anything. Well, oxygen also tends to bond with nearly anything. So having what's called free oxygen, having oxygen available in significant quantity within a physical chemical system is an anomaly, because nearly everything will bond with oxygen and immediately get rid of it from a solution or from an atmosphere. So this was the first case where life changed the planet. When life began, and we talked about this back in September, when life began, it likely began in deep sea vents in an environment where there wasn't oxygen, any significant oxygen to speak of. But after 1 billion years or so, life learned the trick through natural selection of using photosynthesis and carbon dioxide to release oxygen into the air. Well, when this happened, early life, which was primitive and perhaps beneath our notice from a moral or ethical standpoint, that first life on the planet poisoned its own planet, ruined it, by creating oxygen. And when that oxygen got into the water and the atmosphere, it caused all this iron to form, this iron that we use for our industrial society. So on our planet Earth, we largely owe the fact that we have readily available deposits of iron that are technologically useful to the fact that life poisoned itself once, a few billion years ago. Interesting. You begin to see the feedback between life and the atmosphere and the oceans, and that process would not have happened without life. Near that time, also, one of the things that tends to become soluble in the presence of oxygen is not just iron, but uranium. An interesting piece of natural history that just always excites me when I read and learn more about it is there's, in Gabon, in Africa, there's something called the Oklo natural nuclear reactor. Now, it's benign now. It has shut down. But this nuclear reactor arose because uranium, which is soluble in the presence of oxygen, about 1 billion to 2 billion years ago, began to be carried by underground water. And it was actually consolidated and condensed, and you got a collection of uranium-rich minerals in an aquifer in Africa, and it became dense enough that it began emitting its own heat. It became a natural nuclear reactor. That didn't happen before then because uranium wasn't soluble without the presence of oxygen. So life created the first nuclear reactor long before we did. As it turns out, one of the first articles I came across about this particular aspect of my talk today was in, I think, 2012 in an astronomy magazine. And I have a copy of the article here. People can look at it. It's got all kinds of beautiful pictures of gemstones and whatnot in it. And there was this very provocative title, "Did Life Change Earth's Geology?" And at the time, I knew a little bit about geology, but I wasn't, other than the banded iron formations, my knowledge about the relationship between life and mineralogy and geology was relatively more limited than it is now. And this article was one of the things that opened my eyes. This article references a fellow named Robert Hazen, whose book, Earth, the biography, The First Billion Years, I've got a slide of it later, was, again, one of the primary sources of content for the talk today. Amazing idea that life changes Earth and changes even the minerals we see. Calcium carbonate likely would not have formed in any appreciable amount without life. There are all kinds of minerals that would not have formed without life. So you've got compounds of boron, beryllium, mercury, calcium, and other minerals that form amazing compounds and crystals. And many of those, as many as 2/3 of the minerals on planet Earth, are likely not to have existed were it not for the indirect or direct action of living things. 2/3 of our minerals. We have about 4,500 identified mineral species on Earth, different rocks, feldspar and granite and calcium carbonate and quartzite and all of these other kinds of minerals. And 2/3 of them are likely because of life. If you look at a planet that's like Earth in terms of size and likely in terms of original composition, a planet like Venus is likely to have only about 1,500 distinct mineral types. And many of these minerals are useful to our industrial society, not just iron. And if you look at a planet like Mars, it's likely to have only about 500 different kinds of minerals. One of the reasons being that it is so small as a planet that the tectonic processes that sorted out crust material from core material and led to the formation of net new kinds of minerals, those kinds of processes can't happen on Mars. So insofar as humans go to Mars, it's not going to be a rich source of mining new material, depending upon the material. But you won't find banded iron formations, for example. It'll be hard to get useful amounts of iron from Mars, because the geologic processes are often dependent upon the physical aspects of the planet. And life, at least on Earth, has played a leading role. So back to this idea of red Earth. What happened after this great oxidation event? Well, one of the outcomes of this was that new forms of life arose which could use oxygen as their metabolic product, or reactant, and then outgassed carbon dioxide. So it changed the biochemistry of Earth on a very large scale when enough oxygen was evidenced in the atmosphere and when life began to use oxygen. One of the things that happened after the red Earth, about 850 million years ago, so not terribly long ago, there is all kinds of evidence in the geologic record that the Earth was covered with ice. So how did that happen? Well, there was a great supercontinent at the time called Rodinia, and that supercontinent comprised almost all the land on the planet Earth, but it straddled the equator. There was no land up in the northern or down in the southern hemisphere to speak of. And when that supercontinent began to break apart, it made some shallow seas. Shallow seas are perfect for primitive life forms. And the blossoming of life in an oxygen-rich environment caused essentially a thermal blanket to be thrown over the Earth, and you got all kinds more cloud reflectivity, right? You had shallow seas, the reflectivity, which is called albedo. Astronomers call reflectivity of a planet, it's albedo. The albedo of the Earth changed. It became more reflective. It bounced more light back into space. And these vast algal blooms changed the nature of the thermal blanket around the Earth, and it led to the first ice age. And there was nothing to stop the ice once it started. It started in the ocean, it continued south, and by the time it reached Rodinia, or the Rodinia as it was breaking up, it had enough head of steam, as it were, or head of ice, that it just kept going. And if anything, there may have been a small sliver of ocean still available. This was one of the great extinction events in the history of the Earth. Living under ice-capped seas is very difficult. So life, once again, was implicated in a drastic change of the planet. So this notion that the planet and life always work together to keep things habitable and persistent, geology gives a lie to that. Here's two events where life has changed the planet so much that life itself nearly went extinct. So today, when we hear arguments about global warming or climate change that say, well, humans, we are just so small. There's no way that humans can affect the planet. It just doesn't make any sense. I mean, you know, there are quite a few of us, but there are far more earthworms and there's far more fish. Humans, there's no way that we can change the planet. Well, microbes change the planet. They're even smaller than we are. And in terms of their intentionality and their awareness of potential outcomes or impacts of their action, they have none. There's no forethought to anything they do. They're just doing their thing, metabolizing. And they changed the earth and poisoned it twice. Once with fire, with red earth, with oxygen makes fire possible, by the way. So you could say that Earth once died, nearly died because of the fires, and the second time nearly died because of ice. Well, about 100 million years after snowball Earth, one of the things that had begun to be significant were volcanoes that poked up through the ice and emitted a layer of ash. Well, ash tends to be very dark. So this bright, shiny, white, frozen snowball Earth kept reflecting sunlight back, which maintained it in its snowball condition until enough ash accumulated that it diminished the reflectivity of the planet. Furthermore, the gases coming out of these volcanoes made a new CO2 blanket and caused global warming. And the Earth actually swung, swinged it radically from snowball Earth to hothouse Earth. One of the warmest periods in the geologic record happened very soon after snowball Earth. So the balance scale flipped wildly from things are almost too cold to life to things are incredibly verdant. The level of oxygen in the atmosphere went up to something like 28%. Today it's 21%. So you start to see when life exited the seas and things like insects became relevant on land and in the air, you see dragonflies that are this big in the fossil record. All of this available oxygen allowed for super large organisms. The metabolic processes of the Earth were deeply impacted by life. And for the last 542 million years or so, we've had what might be called the green Earth. This notion that the Earth has existed in a form that we might readily recognize. Except some of the species were different. We have some of these dinosaurs around. And the continents were in a different location, and there were different numbers of continents, etc. But from a gross overall standpoint, the Earth for the past 542 million years has been largely recognizable. This notion that the Earth can change drastically between a snowball and a jungle, between one set of geologic processes and another, and that life plays a role in this, this is all implicated in this notion of tipping points. And there are geologic, atmospheric, oceanographic kinds of tipping points that are relevant to the history of Earth. You may remember from my talk about the abiogenesis, the origin of life from non-living material, that in many cases, to go from one state of existence to another state of existence, there is a barrier. In the case of chemical reactions, it's an energy barrier. But you can think of this as any kind of landscape that has a kind of intellectual landscape about the processes that a particular system supports or the particular state of existence of a complex system. A given system can have perhaps many different ways of being, many different ways that are almost stable, if not indefinitely stable. But sometimes those ways of being are separated by barriers that must be traversed, and in some physical sense might be difficult to be traversed. Chemical reactions exist at different plateaus of energy, and they have things called activation energies that must be overcome to get from one plateau to another. Similar with the states of Earth. So here we've got our pale blue dot. That's the Earth. And we've got this landscape of being where Earth could exist in any number of potential contexts and situations, having any number of properties. And Earth can move along this path in a kind of metastable equilibrium. Maybe there's one area where you've got a waterless, gray kind of Earth, and then something happens. It could be the impact of life, it could be the impact of a meteor, and then you've got a different kind of Earth existing in a different kind of metastable equilibrium, and it moves back and forth, but largely remains unchanged until some other event happens, and now Earth looks very much different. Or maybe it becomes a desert world, because a completely new state of being has become relevant for the Earth. And maybe something else happens then that sends the Earth plummeting into a form that we would not even recognize as being the planet Earth. So many of the metastable states in the possible ways the Earth could exist are driven by life. And life can overcome some of the barriers and push it into a completely new state of being. It very well could be that humans play a role in that kind of pushing, and we'll talk about that in a moment. So I want to talk just a moment about the water cycle. This is probably the story that you learn in school, that sunlight evaporates water from the oceans, which rains on the land and causes erosion, and goes into rivers and streams and back out into the ocean, and then evaporates and comes back on the land, etc., right? An endless cycle, the water cycle. Well, geologists have found that the water cycle is far more complex than that picture depicts. One of the things that is very interesting, this is so plate tectonics. This is the idea that a heavy basaltic crust, that basalt comes out of volcanoes. It's a little bit lighter than the bulk material from which the Earth is made, but it's still denser than the continents. So basalt tends to be on ocean floors, and it tends to underlie continents. And when it comes into contact with the silicate-rich continental plates, the basalt crust tends to dive under. And it can carry with it some of the crustal material and throw that down into the deeper Earth where it is hotter. But it also carries a very significant load of water. So they found that as basalt and some of the sediments that ride upon it dive into the Earth, it carries a huge amount of water. And the water carried at continental margins by subducting continental plates is implicated in the pressure that builds up that causes volcanoes. So the water cycle, in some sense, drives volcanism. There's also a deep water cycle where water molecules and HO, which is a close relative of water, hydrogen monoxide, gets incorporated into geologic metamorphic processes. So water changes rock. If you look at nearly any kind of rock that you pick up, it's got a significant amount of hydrogen and oxygen in it. Water gets baked into rocks through geochemical processes. Water plays a role in plate tectonics, not just by virtue of carrying water into the deep earth, but it literally lubricates plate tectonics. One of the reasons that plates are as mobile as they are on our Earth is because, quite literally, they are lubricated by water. Interesting stuff. The water cycle is far more complex. Water is implicated in far more geologic processes than just sedimentation, the erosion of material out of the land and off of mountains. One of the things that I found when researching this is that in the upper mantle, depths of up to about 250 kilometers, earthquakes due to dehydration of water-soaked minerals occur. So some of the relatively deep earthquakes from 250 kilometers deep are because of catastrophic dehydration of water-soaked material. So water not only dries volcanoes, some volcanoes, but some earthquakes as well. Water has a very complex story in the context of land as well. These are some of the different colors are some of the major aquifers in the United States. Here's the Great Plains aquifer, etc. And these various aquifers, which are deep, ancient, typically ancient water trapped beneath the surface, are relevant to agricultural processes throughout the world. And we'll talk more about that in a moment. So one of the things that water does is it weathers the land. It rains on mountains. The steeper and the taller the mountain, the more of its surface area is available for weathering. So that's a kind of negative feedback loop. The taller a mountain grows, the more it weathers. So as there's a rock cycle, as it rains, it washes sediment into the sea. Those sediments grow into sedimentary rocks as they get more pressure. The continental shelves carry those sedimentary rocks into the deeper earth, where metamorphic processes can change them into different kinds of rocks. Sometimes they melt and the heavier materials are separated from the lighter materials at an atomic level, and you get basalt coming out again. So there's a kind of rock cycle that happens as well. It's much slower than the water cycle, but it's still relevant. And plate tectonics, again, plays a critical role. So now I want to talk a little bit about human impacts, right? The Anthropocene, the age we are in, the geologic age where humans are relevant. How are we relevant? What's going on? What's changing about the Earth? So this is a view of some of the aquifers I mentioned, and this is a global view. How to interpret this? So the red area, this is just the shape. So this is the same aquifer redrawn in a larger shape. This is the amount of refill that aquifer gets from natural processes per year. And this is the amount of water demanded or extracted from that aquifer in the same given year. So the rate at which many aquifers are being emptied is much greater than the rate at which they're filling up. There are some exceptions that are notable. The blue regions on this graph comprise aquifers that are filling at least at the same rate as they are being emptied. But many agriculturally relevant aquifers, like ones in the Middle East, in India, and in the United States, are emptying out much faster than they're filling up. This is the High Plains aquifer that I mentioned a moment ago. The rate at which water is being extracted is, looks like it's about 2 or 3 times the rate at which it is being replenished year to year. So humans are beginning to have an impact on even some of the deep water available to planet Earth. And it might even be implicated in some of the earthquakes, right? As you change the hydraulic pressure of water in relationship to rock, you change the geochemical and geophysical structure of the underlying planet. And you can, not likely to cause volcanoes, but modest earthquakes. Deforestation. I learned an interesting thing. Beginning in 2014, do you know the country that is responsible for the greatest amount of deforestation in the world? You might think it's Indonesia. You might think it's Brazil. It's actually Canada. But there's an interesting bright side to that story. Canada is also replenishing, intentionally planting trees such that its net flux of the number of trees over time is essentially constant. So Canada has implemented essentially sustainable forestry policies. I'm not an expert in forestry. There may be still concerns about it that I don't know. But at least in terms of number of trees growing versus number of trees being harvested, they've about struck a balance. Unlike places such as Brazil, which is clear-cutting land so that often poor people can have a little farming plot to feed their family. Turns out jungle soil, though, isn't all that rich for various reasons. And so they move on, and to feed their family the next year, they have to move on to different soil. So we can, from our lofty, wealthy position in the Western developed world, say, well, they shouldn't be doing that, but they have to feed their children. It's a complex problem, complex feedbacks. What are we going to do about it? This is the net rate of deforestation. Canada essentially is a wash. The United States is actually increasing its forest cover through time. The red dots are places in the world where there's significant net forest loss. You see Indonesia, you see Brazil, some of the typical suspects. Ocean acidification. One of the things implicated in climate change is more acid, carbonic acid, etc., in the oceans. That has implications as well. The last time we saw a significant increase in the amount of ocean acidification was something called the Paleocene-Eocene thermal maximum, when global temperatures went up by about 10 degrees on average, 10 degrees Fahrenheit, globally. That's even greater than what is anticipated over the next couple hundred years from anthropogenic global warming. And there were amazing consequences on life. Coral reefs died out at a huge rate. And when you get coral reefs dying out, that can impact the planet. Look at the number of coral reefs across the planet. And coral reefs are the jungles of the oceans. Much of the biodiversities of the seas come from coral reefs and the ecosystems they support. Well, coral is built up of carbonate materials. And when you start having ocean acidification, the shells and the coral, the chemical formulation of these is hampered because of the acidic ocean. And we see that in the fossil record. We also saw in the historic record, in the geologic record, that breaking up the supercontinents at various points in Earth's history caused ruptures into which volcanoes spewed CO2. And that CO2 was implicated in this great global warming event from the Pliocene-Eocene thermal maximum, which was 56 million years ago, by the way. All right, so let's talk a little bit about prairie land. One of the things, we had a talk about this here, Science Sunday, a couple months ago. Somebody was talking about prairie land and desertification, etc. And one of the things that's interesting about natural prairie land is that the indigenous prairie grasses have roots that can go down about 9 feet and keep the soil aerated, keep the mineral content of the soil enriched. And when we replace those natural tall grass prairies, with food crops, we have to artificially maintain the fertility of the soil, and the depth to which the roots of food crops go is much less than 9 feet. So a lot of the deeper action in the soil bed that might happen biologically, naturally, is impeded. This is a view of the extent of both tall and short grass prairie in the United States as estimated when white settlers first arrived in the 1600s or 1400s. And this is the extent of tall grass prairie now. There's a few little dots in Illinois too that are hard to see. So humans are having an impact on an ecosystem large enough to comprise a significant noticeable portion of a continent. We estimate that the amount of tall and short grass prairie remaining from the native, from the original amount is 1 to 4%. And prairie, especially at its margins, is particularly vulnerable to desertification. Right? So one of the things that delineates the boundary of some of this prairie is desert-like or much more arid land. So that land tends to be relatively fragile from an ecosystem standpoint to begin with, and it takes a lot of artificial actions on the part of humans to keep it viable. Remember that aquifer that's under here? We have to pump the water out of there. We have to get nitrogen fertilizers. So we're having an impact. Speaking of the impact, I went to Egypt in 2001, and one of the things that was pointed out to me was that some of these artifacts that are thousands of years old, you see all this crumbling down here at the bottom? Well, that's not because the stones are heavy. That's because of the Aswan Dam. So the damming of the Nile River caused the water table in Egypt to rise, and the water has a certain salt content, and that salt is leaching into the limestone of some of these thousands of years old monuments, and the leaching of salt is causing the limestone crystal matrix to decay, and you're seeing, for the first time in thousands of years, many of the stone monuments in Egypt are beginning to literally fall apart because of the Aswan Dam. So many of our human constructs are having unintended consequences. One of the biggest and most prominent in the news is climate disruption. You see different views of the summer and winter ice caps over time, across time. It's predicted that relatively soon the Arctic will be so denuded of ice in the summertime that you could send freighters directly from Russia to Canada without having to go around the long way. The Northwest Passage, there was back in the 1700s and so, all kinds of explorers were looking for the Northwest Passage that would go from the Atlantic to the Pacific without having to go around South America. Well, we're likely to get one soon. But there are implications for that. Global climate change often takes the form of warmer local climates. This is a projection of temperatures in California for the next 100-ish years. So it's projected that California will continue a warming trend. Up to 100 degrees Fahrenheit to 110 degrees Fahrenheit in areas that are now 80 to 90 degrees. I got drawn into the dark side of the internet this week, and one of the things I found was there are people there that are talking about global warming being a liberal fantasy. I don't think the person understood what the definition of fantasy was and how that is a counterpoint to reality, to things that are borne out by evidence. The amount of evidence for global warming, for climate disruption, is overwhelmingly convincing. And this guy certainly knows about it. Here's another thing that is very interesting. Anybody know what this is? Good guess. It is not a sinkhole.
It's in Russia, isn't it? In Siberia, with all these massive holes in it.
Right. So beginning in about 2013, 2014, these are humans, these massive holes started showing up in Siberia. So some people think that it's aliens that are coming to take samples of the permafrost for some alien reason. Some people thought maybe it was a government project, maybe the Russians are building new silos or something. Well, it turns out that there's a natural explanation, and then that natural explanation involves this very interesting thing where it gets so cold in the Arctic that methane gas gets incorporated into ice, called methane hydrates. And those minerals tend to be very volatile. if you get above a certain threshold in temperature, they can explosively outgas. This is an explosion caused by permafrost warming up and crossing a tipping point. And these holes are showing up in many places across northern Russia. They may someday appear in northern Canada and Alaska as well. And as if permafrost and the Arctic were not scary enough, because methane is a much, much more potent greenhouse gas. Talk about positive feedback. The more the Earth warms, the more methane gas gets released into the atmosphere. The more methane gas gets released, the warmer the Earth gets, which releases more methane gas. One of the great extinction events in the history of Earth has as one of its most plausible explanatory causes a notion that there was catastrophic outgassing of methane across the planet. What if that happens again? It's hard to breathe methane, and not pleasant. Well, methane hydrates are also very common at continental boundaries underneath the ocean. There is more methane locked up in ices along the continental shelves of the Earth than there is in any commercially viable geologic deposit that we can sink a pipe into. The amount of methane is astonishingly high. And much of that methane was created by biologic processes, but it's safely sequestered away in ices and rocks and buried under sediment until it gets too warm. Back a few years ago, I was a little rushed to get this done. I was ill for a couple days earlier this week, so I didn't do all the research I wanted. But you may remember a news story from a few years ago where people in New York City smelled sewer gas, and nobody, for the longest time, could figure out what was going on. There was no ruptured main. There was no proximal human-related cause for people smelling sewer gas in Manhattan. Well, I didn't find the story that corroborates this, so I can't cite it, but I recall that eventually they decided that the reason people in New York City were smelling sewer gas was because some methane hydrates on the continental shelf out beyond New York State had released a large bubble of methane. So it's starting to happen. And one of the great extinction events on the Earth, again, was because too much methane got in the atmosphere. Here's a view of that same thing in the wintertime, to give another sense of scale. So the Earth exists in something called an unstable equilibrium. Almost no matter what state it exists in, there's always some new state of being, a state of existence that it can jump into. This idea that the Earth nurtures us and that life nurtures the Earth and this system that is perpetually self-sustaining is a myth. Earth can lurch from system metastability to system metastability, and humans are beginning to impact that with our new geologic age of the Anthropocene. We have the ability to choose whether we want to have a paradise or whether we want to live in hell on Earth. So this idea of choice, the idea that humans play a role in the active management of our planet and its processes, its physical, chemical, climatic processes, climatic. This idea is driving the second half of my talks this year. So I'm going to leave behind what we would call some of the hard sciences. I'm leaving behind geology and chemistry and physics. And from here on out, starting next month, I'm going to talk about topics that concern how do humans work together? How do we separate the chaff from the wheat? How do we recognize sense from nonsense? What is scientific skepticism? What is science versus pseudoscience? Why is economics important? There are all kinds of misconceptions that people have about economics. So one of the talks coming up in the next couple of months is going to be about basic economics. What's a comparative advantage versus a competitive advantage? Why is it important to know about that? What's global free trade all about? So as we human beings look for mechanisms to have some positive impact on our planet and the quality of life of other human beings, it's important to recognize some of the larger sciences that specify the way humans work together to bring about better outcomes, how we understand the world, how we separate what's truth from fiction. And next month, I'll start with a talk about political science and liberalism and its progress through history. These are some of the books in my library that have been, that I've referenced as I've learned material for today's talk. This is the one by Robert Hazen, largely talking about mineralogy and the impact of life on Earth's mineral history. This is The Story of Earth by Robert Hazen. You probably can't see this very clearly on this book. It's a Pulitzer Prize-winning book from, I believe, it was written during the 80s and 90s as a series of books. It's called The Annals of a Former World by John McPhee. Some of you may be familiar with John McPhee. Elegant, beautiful writer about history and nature. So these are good books for that topic. And that's it. Today is Gaia, the planet life created. Sorry, I misspelled it there. And this is what we're going to talk about from here on out. Political science and liberalism, economics, critical thinking and scientific skepticism, the practice and practitioners of science versus pseudoscience, and then wrapping up the year with some unsolved scientific mysteries. And that's it for today. Thank you very much for your time. Any questions? Yeah.
Excuse me. Comment. This week I read an article. We're talking about humans change. They say 6,000 years ago, life on Earth, it was in, I won't say two states, that's the wrong word. Life is either commingled or it's isolated.
In terms of human communities, or?
No,
Oh, okay.
all life.
Okay.
And they said starting about 6,000 years ago, humans started to influence it. What was predominant back then was to be commingled. Different life lived in the same area and survived with each other. And since humans started 6,000 years ago, it has gone the opposite way. Now there's more isolated life forms than being commingled.
Like monocultures of crops and fields of animals.
Right, the animals, for whatever reason, maybe too much competition now in one area, they can't exist together anymore. I think that's separate.
Okay.
The other thing was a comment on ocean acidification. The key problem goes to that is the rate of acidification. It's not the fact that the ocean's becoming more acid, because life can exist there, but it's the competition for the carbonate. So when the acid forms, it takes the carbonate out of the water. There's no carbonate there for the animals to form the shells.
Okay.
So it's the lack or the competition for the carbonate that's causing the big problem.
And rates of change are implicated.
As opposed to the pH.
Okay.
There's an island in the Mediterranean off the coast of Italy, which I guess naturally occurring because of volcanic activity. There's acidification occurring. Acids are being poured into the around the coast, and they've done like a 20-25 year study. The way the currents go and how things go, you can measure gradual change as you go along the coastline of this island in the Mediterranean. And a gradual increase in acidification means this decrease in what species can live there. And so they can have a very accurate representation of what occurs. This is occurring because of concentration of acid and lack of capacity, but mussels and clams and different animals that have to make their shells have these like horrendous holes in them, in the midst of them. They can't produce their shells properly, and they can measure it along the coastline of this place, which you can then maybe extrapolate to time as the oceans acidify. It'll be more like this, so measured concentrations that are fairly stable around the coast of this island, which gives them a pretty good picture to extrapolate what can happen as the oceans continue to acidify.
Mm-hmm.
Sure.
Yeah.
When you said that Canada is sort of deforestation, but they compensate it by replanting new trees, but I presume that is the number of trees is constant, but the new tree you plant is much
Right.
more than the old one to count. So in fact,
Right.
the effect is much worse. But of course, with trees which take out carbon from the atmosphere, but when they rot or are burned, they put it back in. So that's a sort of neutral, carbon neutral thing.
Right.
Still, deforestation is pretty bad, especially in the Amazon from the point of view of ecology.
Right. And then there's the fossil fuels, which are,
Fossil fuels different because they're,
right.
that's-
Yeah, they're sequestered carbon from life that we're releasing again. Yeah.
You mentioned that the first extinction event happened 800 million years ago before the Cambrian exploded. How was that corroborated? We know that those the life forms weren't well preserved before
Right.
the Cambrian exploded. So it surprised me that.
So a couple years ago, I gave a talk. I'll probably do it again in a year or so because it's a good topic about the science of dating. And I didn't have many teenagers who came to that talk because it was about chronological dating. How do we know the dates of the things that happened? And one of the things I talked about there was how radiocarbon isotope collection and measurement can help us put dates on things up to about 6,000 years ago. But it turns out that life is fairly consistently lazy, and life uses carbon, right? So one of the signatures of life being present in a geologic context is if you get a lot of lighter carbon in your carbonate rocks, it tends to indicate that life has been selecting because of its metabolic processes for that lighter carbon. And through time, as you see the amount of carbon-12 versus carbon-13, not 14, which is for radiocarbon dating, but as you see carbon-12 versus carbon-13 in geologic signatures of the rocks, you can infer how active metabolic processes were across the planet at that time because life preferentially sequesters carbon-12. If carbon-13 is a little heavier, and because life is lazy, it doesn't want to use the heavier atoms, it uses the lighter ones, and so that kind of carbon tends to get sequestered. So it's not really radiocarbon dating per se, but looking at carbon isotopes between 12 and 13, they can find when and by which degree life was active in the biosphere in a given geologic strata. And by the way, that's one of the more indirect but pretty persuasive pieces of evidence for life arising within a couple 100 million years of Earth's formation, as you begin to see that differentiation between carbon-12 and carbon-13. Does that answer your question?
Yeah. So it was not like counting organisms
Right.
in the layers, but
It's the carbon signature.
Yeah. Now, a follow-up question. So, where does the water on Earth come from? Scientists believed until recently that comets are mostly responsible for that, and because beyond the other planets, Neptune, there's a Kuiper belt in the Oort cloud, there's a huge water reservoir, and the Earth was bombarded by comets for a long time. Also, people think, but it turns out that the isotope ratio, so heavy water to light water in comets, doesn't match the profile. It's a recent finding. So what is the best explanation for water on Earth?
So the answer I'll give isn't more informed than yours. I've heard comets are implicated, but there's also indigenous water locked up in some of the mineral grains from their primal solar nebula. But I could take the question a step back. It may not be answering the question you asked, but it might still be relevant. When stars bake different elements to make the stuff that we see around us, the carbon and oxygen and whatnot, it turns out that oxygen and carbon are some of the most common elements in the universe, and hydrogen is certainly the most common. Well, water just being 2 hydrogens and 1 oxygen atom should and is fairly ubiquitous in the cosmos. So at a very primal level, the water on Earth came from the fact that there was a lot of oxygen and a lot of hydrogen in the solar nebula. Now, how that got incorporated into the mineral grains that formed the Earth, I talked about the fact that if you look at nearly any mineral, you will find hydrogen and oxygen. You'll find hydroxyl groups in the mineral signatures, the chemical formula for the minerals. And through different physical heating processes, different pressure continuums, and different mechanical weathering processes, you can get water out of rock, just like Moses did. Well, probably nothing like Moses did. And so that the fact that hydrogen and oxygen together came as part of the Earth isn't surprising. It may have been locked up in minerals, and the particular geologic, geochemical process that released that as water vapor from volcanoes, I'm not an expert in. But between outgassing from volcanoes of locked-in water and comets, I suspect that's where a lot of the water came from. But I don't know definitively. Other questions? Yeah.
So we see here a broad pattern of a series of semi-stable states in which Earth has been different semi-stable climates, and there's a barrier between between them. But it seems to be we've gone through several in a million years. Could be more later. Whereas I note Venus appears to be stuck in one.
Right.
Anything special about like that event or
Yeah.
Is there
Okay. So one of the things that differentiates Earth from Venus is plate tectonics. And I've in several different talks, I think there was one last year, and then certainly the Drake equation discussion I've had previously. I've talked about how plate tectonics is a critical aspect of the geologic and almost certainly biological evolution of the Earth. But plate tectonics may be a lucky happenstance of the fact that the moon formed from a collision with another astronomical body. We on Earth are fortunate to have a relatively thin crust that gets us all kinds of fun things like volcanoes and earthquakes, which, I mean, how entertaining would it be without those? But the relatively thin crust of Earth allows for the formation of plates. There's also, Earth is large enough that it's got convective currents of magma inside it. Mars isn't big enough for that. Those convective currents in Earth are largely driven by radioactive decay. So the Earth is a giant nuclear reactor still. Venus is about the same size and likely has similar heat trapped in it, but it doesn't have the thin ductile crust that can move around and cause a rock cycle to happen. So a lot of the dramatic changes in Earth's geologic history have been because of breakup and formation of continents and the interaction between continents and the seas and continents and the air. So I personally think that plate tectonics is absolutely critical for a thriving planet that supports a diverse ecosystem, but it gives rise to periodic chaos as well. Other questions? Yeah.
So the acidification of the oceans, as I understood it, the CO2 that being absorbed is supposed to go into, they thought it would go into the atmosphere and the planet on it, but it actually does, so it ends up getting absorbed in the ocean.
Some does, not, it's not an all or nothing thing.
And then that changes the pH level.
Right.
The Gaia hypothesis is pretty weird, though. reminds me of the anthropic principle.
It does, yes. Yeah, the anthropic principle says essentially that the universe, we exist in this universe because the universe exists in a special configuration that lets us exist. It's kind of this bootstrapping idea, and there's a strong and a weak anthropic principle. But the Gaia hypothesis does have echoes of that we live on a special planet, and this special planet is conducive to life, and life
Maybe the galaxy.
propagates.
could be
Right.
an organism.
Yeah, where does that stop, right? But if you look at the catastrophic changes, the snowball Earth and red Earth and hothouse Earth, if you look at the catastrophic swings in the geologic record, it kind of puts the lie to the idea that life and the planet live together in symbiotic harmony perpetually. Life nearly died a couple times, and certainly the Earth, physically and biologically, has changed radically many times over its history.
But it's a means of mankind, humanity trying to bring purpose to
Right.
existence.
And in its most insidious form, the form that bothers me the most is, well, there may not be a God that's keeping watch of the planet that fixes anything we mess up, but the planet is so big and so integrated and so loving that no matter what we do, the Earth will rebalance itself. I don't believe it, and the evidence doesn't support that contention. All right, thank you very much. I'll be available for more discussions.